we study two special sequential circuits. The first one is counter, and the second one is the register. The counter is a sequential circuit that counts number. So for example, so we can design a circuit like that will be counting 2, then 3, then 7, then 4, then after 4, then it again go to 2, 3, 7, 4, 2, 3, 7, 4. So this way, this counter will be counting 2, 3, 7, 4, 4 forever, as long as the device has the power. So there are two types of counter. The first type we call asynchronous counter. Or also it is called ripple counter. So in this type of counter, the output of a flip-flop is used as a clock pulse of another flip-flop. So on the other hand, for the synchronous counters, so there is a common clock pulse for every flip-flops. So these asynchronous counters are very difficult to design, and we'll study this asynchronous counter a little bit. We'll also study detail the synchronous type of counter. Let's consider we have two flip-flops. D flip-flops. And let's also consider that these are the positive edge triggered flip-flops. So we have here, let's consider this one is Q1 T, Q1 T plus 1, Q2 T, Q2 T plus 1, and also that this guy is connected there. Similarly, that guy is connected. And also that this switch also connected. These two connected to the clock pulse, and that's the input clock pulse. The clock pulse for the first flip-flop comes from external. On the other side, the clock pulse for the second flip-flop comes from the first flip-flop. Now we want to analyze this circuit, this simple circuit. So it has two flip-flops. It doesn't have any input, no output, but only the current stage and the next stage. So we got Q2T, Q1T, then we got Q2 T plus 1, Q1 T plus 1. Consider we have 0 0 0 1 1 0 1 1. So now see if we have Q2 0, Q1 also 0, Then so when the input clock pulse goes from 0 to 1, the first flip-flop is triggered, and when the first flip-flop is triggered, then the reverse output of the first flip-flop goes to the input of the same flip-flops. So and we also know that Q1 is 0, so Q1 prime definitely 1. So then the output of the first flip-flop changed to 1. This is 1. Then the clock pulse for the second flip-flop, it changes from 1 to 0. So it doesn't get triggered, so the second flip-flop doesn't get changed. So now, so if we have Q2 0 and Q1 1, Q1 we have 1, so this is 0, so then what happens? So when the clock pulse goes from 0 to 1, then the first flip-flop is triggered, then the output of the first flip-flop is changed to 0, and the clock pulse for the second flip-flop goes from 0 to 1. So the second flip-flop is triggered, and then the reverse output of the second flip-flop goes to the input, and we know that is 1, the reverse output is 1. So the second flip-flop, the output of the second flip-flop will be 1. Now let's consider for the third combination. For the third combination, we have 1 0. So we have Q2 1 and Q1 0. Similarly, we have Q1 prime 1 and Q2 prime 0. So when the first flip-flop is triggered, or it goes from 0 to 1, then the state of the first flip-flop is changed from 0 to 1. So that gets changed. That gets changed to 1, and this becomes 0. So Q1 is changed to 1, and the clock pulse for the second flip-flop becomes from 1 to 0, so it doesn't get triggered, so it doesn't change. So now for the very last combination, so that we have, so we have Q1 1, Q2 1, and Q1 prime 0, Q2 prime 0. So when the first flip-flop is triggered, or it goes from 0 to 1, then the output changes, and the output becomes 0. It is it becomes 0, the output of the Q1, and that becomes 1. And the flip-flop for the clock pulse for the second flip-flop changes from 0 to 1. Then it's also triggered. Then this 0 goes to the input, and it becomes the output, so it gets 0, and then again it's 1. So we actually have 0 0. So that's the total function of this small circuit. Now if we consider that we have 4 states here: 0 0, 0 1, 1 0, 1 1. So then what's happening here? So if the present state is 0 0, then the next state is 0 1. If the present state is 0 1, the next state is 1 0. If the present state is 1 0, the next state is 1 1. If the present state is 1 1, the next state is 0 0. So that's how it's getting 0 0 0 1 1 0 1 1. And again 0 0 0 1 1 0. It doesn't have any input, only the state transition from present state to the next state. Now, so we know that this 0 0 is actually 0, in binary representation. So similarly 0 1 will give us 1, 1 0 will give us 2, and 1 1 will give us 3. So 0 1 2 3, then again 0 1 2 3. That's how this small circuit will be counting this sequence of numbers 0 1 2 3 0 1 2 3. That's how it continues. Now, so if we want to add so more flip-flops here, okay, so yeah, this is actually called is a 2-bit ripple counter. Now if we want to make a 3-bit ripple counter, that process is easy. So we only need to add another flip-flop here, and this input of the flip-flop is connected to the reverse of the output, and also that guy comes as a clock pulse. So we have D, Q, C, and then Q prime. And now we get here, this one is Q3 T plus 1, and that one is Q3 T. So now if we analyze the functionality of this circuit of 3 flip-flops, then it will actually give us a sequence of counting from 0 to 1 0 1 2 3 4 5 6 7 then again, so from 7 to 0 1 2 3 4 5 6 7 0 1 2 3 4 5. So that's how it will continue. So now if we want to make a 4-bit ripple counter, then we need to add another flip-flop, and the 4-bit ripple counter will count the sequence from 0 to 15, then again 0 to 15, 0 to 15. That's how it will continue. So we actually can make such counters by as many flip-flops as we need. So if we want to count from 0 to 31 or 0 to 63, so we only need to increase the flip-flops. And also is the ascending order of counting 0 1 2 3. Now, so if we want descending order counting, like 3 2 1 0, 3 2 1 0, the reverse order of counting, then we can change the positive edge triggered flip-flops to negative edge triggered flip-flops. If we are going to change all the flip-flops to the negative edge triggered flip-flops, then this circuit will start counting in reverse order, and demonstrate this functionality yourself at home. Asynchronous counters are very difficult to design. Now we study synchronous counter. Synchronous counter has a common clock pulse, as we saw for the asynchronous counters. The output of a flip-flop becomes the clock pulse to another flip-flop. But in this case, the asynchronous counters are common. So we need to find the state table for any counter. And if we can find the state table and we know that, so we can design the sequential circuit. Let's see this with an example. Like we want to design a circuit that will be counting 2, then 0, then 1. This sequence will be counting 2 0 1 2 0 1 2 0 1, and we also know that we represent 0 by 0 0 in binary. We represent 1 0 1. We represent 2 by 1 0. So this is the counter that we want to design. So we will need 2 flip-flops, definitely 2 flip-flops. So now we have the state diagram, and we want to find the state table. So in this case, we don't have any input, no output, only the present state and the next state. Let's consider 2 flip-flops Q2 the present state, and Q1 present state, and then Q2 next state, Q1 next state. Zero, 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 one, 1, 0, 1, 1. So if the present state is 0, 0, present state is 0, 0, then the next state is 0, 1. So we got 0, 1. 0, 1, 1, 0. Then 1, 0, 0, 0. If the present state is 1, 1, then it is not defined in the specification. So we can consider it them as don't care. And we know that don't cares actually give us flexibility in designing simplified and optimized circuit. So now we got the state table, and we want to design the circuit, and we need to know the functions for Q2 t plus 2 and also Q1 t plus 2. So now we need a truth table. Q2t, Q1t. And this is for Q2 t plus 1, the truth table. So we have 0, 1, 0, don't care. So 0, 1, 0, don't care. So we can consider this pair, and then we will find Q1 t. It's a small equation. It's a very simple equation. And for the second equation, so we need another K-map. Q2t, Q1t, 0, 1, 0, 1, and we got 1, 0, 0, don't care. 1, 0, 0, don't care. So we don't need to consider the don't care in this case because we only have this one, only 1, 1. So Q1 t plus 1 will be Q2 prime t times Q1 prime t. Now we have the equations, and we want to draw the circuit. So we need 2 flip-flops. Let's consider the first flip-flop is Q2. The second one is Q1. So now we got here D and the clock pulse, D and the clock pulse it has a common clock pulse. Then we have Q prime, Q prime, and the Q prime is there is a purple here. That's Q t plus 1 Q t. It's not Q, it's Q2, and also other side we got Q1 t plus 1 Q1 t. So now what is the equation for Q2? For Q2 t plus 1 equals Q1 t. So we have Q1 t here. So if we just connect that here with this one, then the first equation is implemented. For the second equation, we need an AND gate for Q1. So we need an AND gate. The first input is Q2 prime. So the Q2 prime we can bring from here. The second input is Q1 prime. So the Q1 prime so you got the AND gate. So now we provide this as input to the flip-flop. So now we have this two Q1 Q2 and also Q1, this Q1. So now, so if we start this circuit operation, and you also have the clock pulse here, then if we do the power 1, then it will start counting the sequence of digit that we already specified. Let's see another example. This example, so we have 0 1 0, then 0 0 0, then 1 0 1 0 1, okay, 0 1 0, again 0 1 0, so we don't need that 0 1 0. So that's 3 numbers it should be counting. Well, so what is the state table? No input, no output, but only the present state and the current and the next state. So let's consider, instead of considering Q1, Q2, so we can also consider X, Y, or we can also consider A, B, C. Let's consider A, B, C in this case. The present state, A, B, C. In the next state, C, T plus 1, B, T plus 1, A, T plus 1. So when it is 0 0 0, then it's 1 0 1. When it is 1 0 1, then it is 0 1 0. When it is 0 1 0, then it is 0 0 0. So again, when 0 0 0, and for the other combinations it's not defined. So and we can consider the other combinations as don't care. So we don't need the state diagram anymore. Now we want to find the functions by using K-map, and we need 3 inputs K-map. Let's find the function for C T plus 1 first. C T, B T, A T. So we have for 0 0 0 1, for 1 0 1 0, 1 0 1 0, 0 1 0 0, 0 1 0 0, and the rest I don't care. So what can we do? So we can consider this one, this pair, or that pair, doesn't matter actually. So this pair will give us CT plus 1 equals to B prime T times A prime T. Okay, so we got the first equation. And for the second equation, so we need another K-map. C T B T A T. So now, so we have for 0 0 0 we have 0. For 1 0 1 we have 1. For 0 1 0 we have 0. 0 1 0 we have 0, and the rest I don't care. So now we can consider these 4. So then so it will give BT plus 1 equals to A T. Pretty easy. Then the next equation, CT BT AT, 0 1 0 0 0 1 1 1 1 0. Now for 0 0 0 we have 1 1 0 1 0 1 0 1 0 0 1 0 0. So 0 1 0 0, and the rest I don't care. So you can get a t plus 1. I think it should be okay. So if we consider this pair, then b prime a prime, b prime t a prime t. So we got these three equations. Now we want to draw the circuit. Okay, we only need the equations now, and we don't need the remaining. Now, so we know that, so we need 3 flip-flops in this case. D, 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 Q, 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 Q prime, Q prime, Q prime, and also a common clock pulse, positive edge triggered or negative edge triggered, doesn't matter actually. It's the clock pulse. Now for CT plus 1, let's consider this flip-flop is C, the second one is B, and the very last one is A. These 3 flip-flops we have. For CT plus 1, we need A prime, B prime, and an AND gate. So we have an AND gate. So we have A prime, and we also have B prime. Then it goes to C t plus 1. CT plus 1. Well, we don't need that equation. So now, then what do we have for B is AT. So for B is pretty straightforward. So we have A here, and then we are only going to connect this A to B t plus 1. Then the very last one is again A prime, B prime. So we already have the A prime, B prime. So then we are only going to connect this A prime, B prime to A t plus 1. So now, so we have C t, B t, and also A t. Okay, so it's CT, BT, AT. So now we have these 3 points, and we have the clock pulse, we have the design. Now if we give power to the circuit, then this circuit will start counting the sequence that we are given, the specification of the design. So BCD stands for binary code decimal. So what is that? So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. These 10 digits in decimal number system. So we can represent 0 by 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, then 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1. So how many we got so far? 1, 2, 3, 4, 5, 6, 7, 8. Then we have 1, 0, 0, 0. Then finally 1, 0, 0, 1. Okay, so this 10 representations. So we do this representation, then we can write any numbers like 5, 7 to this number. What is 5? So 5 means 0, 1, 0, 1. So it's 0, 1, 0, 1. And 7 means 0, 1, 1, 1. 0, 1, 1, 1. Then 2 means 0, 0, 1, 0. 0, 0, 1, 0. So this representation of decimal number is called the binary code decimal BCD representation. So in this representation we have 10 digits, and each of the digit we represent by using a 4 bits binary number. Now we want to design a BCD counter. A counter is BCD, so if it counts from 0 to 9, then again it comes back to 0. So if you have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. It starts from 0, then 1, 2, 3, 4, 5, 6, 7, 8, 9, and again 0, 1, 2, 3, 4, 5. So we can design this counter, and this counter is called BCD counter. Do it yourself at home.